Today we will move into the other compensator in frequency response. Previously we discussed the lag compensator. Today we move into lead compensator. If you look back into your into the previous slide, we see that lag compensator is used to improve steady state error and maintain the transient response. The lag compensator is similar to the case for PI controller. In contrast, the lead compensator that we will discuss today is used to improve the transient response. So we use a lead compensator when we want to improve the transient response. How it can be done, how a lead compensator can improve the transient response, it is done in two things here. Okay, first, lead compensator will increase the phase margin. We know that when we increase phase margin, we can reduce overshoot. Secondly, we want to have a faster transient response by increasing the bandwidth. Okay. So perhaps you are not familiar with bandwidth. Bandwidth is defined as bandwidth related to the gain crossover frequency. So if we can increase the gain crossover frequency, we can at the same time increase the bandwidth of the system. We want a high bandwidth. Higher bandwidth will give a faster response. So lead compensator will also increase the gain crossover frequency and then and thus the bandwidth of the system. Okay. So we can achieve this, number one and number two, by using the lead compensator. This is the transfer function of the lead compensator. GC, just rewrite 1 over beta S plus 1 over T S plus 1 over beta T. And beta is less than 1. So beta here less than 1. Meaning that the value here is less than 1, is bigger. This value is big, is bigger than here, then 1 over. So small value. The pole is smaller than the 0 here, because beta less than 1. So you have to remember this. You have to memorize this formula. I'm not sure whether it will be given in the exam or not, but to be sure, please, you have to remember memorize this. 1 over beta S plus 1 over T S plus 1 over beta T. Therefore, two variable here is beta and also T. We need to find beta and also T. This is how a lead compensator works. Let's see the black one, uncompensated system, which is the system without controller. Here also uncompensated for magnitude and phase. In the figure here, the uncompensated system has a small phase margin. So this is the phase margin of the uncompensated system. Okay, this is the gain crossover A, and then here is the phase margin at B, right? We want to use lead compensator to increase the phase margin and also to increase the gain crossover frequency. Here now gain crossover is at A. Gain crossover A, phase margin B. Using the lead compensator, this is the lead compensator. Lead compensator is like this. You will see in detail later. This is lead compensator, like this, right? If you notice, it is opposite to lag. Lag going down like this. Okay, this is lead, and the phase is like this. The phase for lead is also going up 90 degrees here. The lag, it is lagging, going down. So when we increase lead compensator, this is compensator. Here also compensator for the phase. If we add together here, compensator plus uncompensated system, we have the compensated system here. And this is the compensated system. Now, A, the gain crossover, now increase to C because we add lead compensator. Then we achieve one of those, the requirement, which is to increase the gain crossover frequency from A to C. Then here is the new phase margin in which we increase from B to D. When we increase phase margin, then we can reduce overshoot. So this is how how lead compensator can be used to achieve both, which are increasing gain crossover frequency and also increasing the phase margin. As the transfer function, 1 over beta S plus 1 over T, 1 over beta T. If we plot in actual one, the magnitude is like this. This is the magnitude and this is phase. You can see it is dependent on beta, dependent on value of beta. Beta 0.1, 0.2 until 0.5 here. Here also 0.1 until 0.5. This is the plot for the lead compensator, okay, with respect to beta. And they are different, okay, based on beta. And also there is what we call a maximum angle, maximum phase. Okay. They are also depending on the value of beta. Okay, let's move. In designing the lead compensator, you have to know first the transfer function that I discussed just now. And there are three important formula which you also need to know. First one, we call omega maximum. Omega maximum is equal to 1 over T square root beta. I think it will be given in the exam, but it's good if you can memorize this. First, omega maximum, which is the frequency at maximum phase angle, 1 over T square root beta. Next, the second equation is we call maximum phase angle, phi max. Phi max is sine inverse 1 minus beta, 1 plus beta. I should write here. I rewrite here. The last one, we call the compensator magnitude at omega maximum. Magnitude GC at omega maximum. The magnitude is shown by this symbol. Magnitude is 1 over square root beta. These are three important formula which will be used in designing the lead compensator. Let's see how it works, how we can use this formula. You can see that we just now I show the dot plot for the lead compensator. They are depending on beta. We can see that let's choose one value, beta 0.1. If we take beta 0.1, we can calculate for phi max. Phi max and sine inverse 1 minus 0.1, 1 plus 0.1 is sine inverse if we calculate, becomes 0.8181. And the inverse is 54.89. 54.9 degrees. And and the magnitude, if we calculate here, omega maximum is 1 over square root 0.1, square root 0.1, 3.16, and in dB, this is not in dB. If in dB, equal to 10 dB. 20 log 3.16 equal to 10 dB. That is the case for beta 0.1. So here we calculated and I wrote it here. Beta 0.1, pi max 55, magnitude 10 dB. So we can see here in the graph here at beta 0.1, beta 0.1 here, the maximum phase is here, maximum. The peak is 55. It's similar to this, 55. And at that time, here, the phase, the magnitude is 10 dB. Yeah. So this is to show that the dot plot here is correct and according to the formula. If you do the same for beta 0.5, you will get a phase maximum phase 19.5. 0.5 here, 0.5, 19.5, nearly 20, 19.5. And at the same time, if we look into the magnitude at beta 0.5, it is here, it is 3 dB. Okay, 3 dB. That proves the formula and also the phase, the transfer function and also the dot plot. Let's move on. These are the design steps. I will not read one by one. I will not go through one by one. We will do through example. Okay, how we can do that. Okay, let's move into one example. Now we want to design a lead compensator. Given system, this is the system, use block diagram to design a lead compensator to achieve 20% overshoot and KV40 with a peak time of 0.1 second. So here, meaning we want to improve the transient response. And we can improve the response by using the lead compensator. It is mentioned here, design using a lead compensator. The transfer function, the open loop transfer function here is GS equal to 100K over S plus 36, S plus 100. That is the open loop transfer function by multiplying all block here. If we want KV40, we know that KV is limit S to 0 SGS. If you substitute and solve this equation, you get 100K over 36 multiplied with 100. That is KV, and we want KV equal to 40. Therefore, K to be used is 40, is 3600 over 100. You calculate, it is 1440. This is the value of K in order for us to achieve KV40. Then, therefore, we can plot bot plot with K1440. Therefore, it is good if we can have a bot plot with K1440, such that we get KV equal to 40. Okay, this is a bot plot with K equal to 1440. I replotted using MATLAB. This is the one given in the textbook, the uncompensated system here, the black in color, right? Okay, from here, we can see that the gain crossover is about at this place, about 1 radian. Sorry, this is 100, this is 10, about 30 here. 10, this is 100, about 30, gain crossover. Gain crossover frequency. And we can calculate phase margin. This is the phase margin. If you calculate here, the phase margin is 34 degrees. This is not exact, but the actual is 34 degrees. It's similar to the one given in the textbook. Okay, so this is the one with K1440. We get gain crossover at omega about 30 radian per second, and the phase margin is 34. We will consider this as the original system. Okay, now our phase margin is 34 degrees, and desired overshoot is 20%. What we want from the equation, from the question, is 20% overshoot. 20% overshoot, meaning that we want phase margin 48 degrees. Okay, this can be obtained from the graph of overshoot, zeta, and also phase margin. In order to get 20%, phase margin must be 48 degrees. Okay, now we will start designing a lead compensator. First, we need to obtain the required phase. The required phase is obtained by subtraction 48 degrees. This is the required one, the required phase margin minus the original phase margin. We want this. We already have this is the original. Then we need to add more. The one that we need to add is 48 minus 34. And usually we will also add 10 degree or 5 degree, it depends. We call this as correction factor. In designing a controller in frequency response, we normally add a correction factor. It varies. In the exam, sometimes it will be given the value, sometimes not. You can design by considering a correction factor, or you can just ignore correction factor if not mentioned in the exam. If mentioned, then you have to use. So here, that means we require 24 degrees. We require 24 degrees of phase. By using the lead compensator. We want to use lead to increase the phase margin. Once we have this, we can apply the formula. Use number 2, use the formula. Okay, first formula, we know phase. You can use the second formula, phi max. Phi max equal to inverse sine 1 minus beta, 1 plus beta. We know phi max here is 24. The phase that we want to add. Then, of course, we can solve for beta. One minus beta, 1 plus beta equal to sine 24 degrees. If you solve, you will get beta equal to 0.42. Sine 24 is sine 24 degree is 0.4067. If you solve, you get beta 0.42. That the first formula that we can use. The next, we will use the other formula, the third formula. Third formula is the maximum. Number 3, use the use equation 3. Equation 3 is the magnitude at omega maximum. We know beta, we can just apply, substitute those values. Beta 0.42 It is 1 over 1.5430, and normally we want in dB. So then we get GC J omega max in dB. 20 log this log. It is 3.77 dB. Right? So we have applied two equations. Equation 2, here equation 2 use formula. I should write equation 2. Okay, first equation 2. Then once we get beta, we calculate the gain, the magnitude at omega maximum 3.77. Right. What's next? Next thing we have to do is to use the graph, the dot plot here to determine because what we will do is we will add 3.77 dB. Okay, and we want at omega here be the new gain crossover frequency. In order for this, for omega max to be the gain crossover frequency, we need to find here where omega, where magnitude equal to minus 3.77. Because what we do, we will add plus 3.77. We need to find where it is minus 3.77. So that when they add together, it becomes 0. And it will be the gain crossover frequency. So from here, from the graph, we have to check where minus 3.77. Of course, not easy here. The scale is not good, very small. So we can do here and check minus 3.77, about here. Okay. I will use the one here. Okay, here minus 3.77. Or here I use 3.76. From the graph is here. Minus 3.77. And the one here is 39 radian per second. This is omega. Omega when magnitude equal to minus 3.76 or 3.77 dB. Okay, that means here, if I return back and use this, here is, yeah, maybe correct. About it's about 40. Let's see. Let's assume this is the one. And the value here is 39 radian per second. Here 3.77. So we need to find on the graph where it is minus 3.77, and what we want is the omega here. And we obtain omega at 39 radian per second. Okay, so we find that omega equal to 39 radian per second from the dot plot. Thus, we can use number 5, use equation 1. Equation 1 is omega max is 1 over t square root beta. And the one here that we obtain omega here is called omega max. Okay, that's why it is written here the gain or the magnitude at omega max, and we want to find where it is minus 3.77 from the plot when magnitude equal to minus 3.77 dB. Okay, remember initially positive, now we want negative, so that when we add it becomes 0. Okay, solving this, we know omega max is 39, 1 over t, we know beta 0.42, then of course we can solve for t. If we solve t is equal to not with me, t (0.0395). 0.0396. That is t. Am I right? Okay, that is t. We already have beta. We already have t. Then we can finally obtain the transfer function GC or G lead compensator. G lead is 1 over beta S plus 1 over T S plus 1 over beta T. Okay, you see beta always less than 1. Here we get 0.2. So if you solve, you will get 2.38 S plus 25.3 over S plus 60.2. That is the transfer function of the lead compensator. Any question? If you have question, please ask.
No
And
question, Doctor.
finally, number 6. Finally, we want the final compensated system. We have
Doctor, number 7, right?
number apa?
Final step number 7. Ke number 6?
7. Number 6.
Tadi 5, 6.
5. Okay, 5.
5, 6 and then 7 lah.
Huh?
Yang final step tadi Doctor tulis.
Oh, 7. Okay. Okay, number 7, the final compensated system. We multiply G with GC. G is G here 100. K we know K at 36 100. 100 T 1440 S 86 100. And we need also to multiply with 2.38 here, S plus 25.3 over S plus 60.2. So here is 342,720 S plus 25.3 S plus 36 100 60.2. That is the final system when we add a compensator. If you follow the sequence, number 1 to number 6, number 7, I'm sure you can do it. It's not that difficult. If you see lead compensator is easier than lag compensator. For lag compensator, you have to draw on the board plot. But for lead, you just read data from board plot and apply the 3 formulas. Is the one that we discussed. Also, I wrote in the slide. Okay, this is to obtain the phase margin. Then we get 3.39 radian per second omega max, and this is the final compensated open loop transfer function. Here slightly different. I recalculated. Okay, but this is the actual one taken from the books. Using the compensated system transfer function, I replotted the board diagram again. You can see the blue one here is uncompensated with K1440 without lead compensator. The red in color here with lead compensator. You can see now, initially the gain crossover frequency is here, now increase to here. Okay, from about 30 to here now 39. We managed to design, we increase from 30 to 39 radian per second. And this was, sorry, the phase margin was here, the blue one. Okay. Now, phase margin increase to here. Okay, from here it is about, it's increased. Not that accurate here. If I check, it's about 135, 55 degrees. Okay, we want about 48. We want about 50 degrees. We get 55. Even better. But this is not accurate. But it increased from for the uncompensated into compensated system. We increase first gain crossover frequency, and number two, we increase the phase margin. Increase gain crossover frequency will make a system faster. Phase margin will make the overshoot reduce. Right, that is lead compensator. This is one example. This is a book taken from the textbook. You can try to design. You can use MATLAB to help, because using MATLAB you can just plot you can have the plot and read the data, so you can design easily. You can also try to change the value, use different value of correction factor. Maybe you can try 10 degrees, then you can try 5 degrees. You can see how the correction factor affect the result, the final result. Okay, let's move to one example. Final exam, 2014-2015. Given the board plot here, okay, it's mentioned the transfer function of a hard disk drive has been identified as this. This is the transfer function given in a normalized form, s over 2.5 plus 1, s over 6 plus 1. The position of the system is controlled using feedback loop. This is the system with a feedback loop. And the board plot is given. Use the box plot to design a lead compensator. It is mentioned here, design lead compensator. So that the phase margin more than 45 degrees. Here, the question did not specify exactly 45. It can be more, but at least 45 degrees, because the higher phase margin is better. Okay? And we wish to obtain a steady state error less than 0.1. We want steady state error less than 0.1. Assume that the correction factor, here the correction factor is given 5 degrees. Sketch the box plot for the first design. Number 2, the question also want you to sketch the box plot of the compensated system. And then number 3 is just a theory question. What modification you can propose if the lead compensator cannot meet the specification? This is just theory. Okay, let design. This is the box plot. So given, let do together. GS here was 10K, S 2.56, S over 2.5 plus 1, S over 2, S over 6 plus 1. If we can write in a familiar format for us. This is in a normalized format. We can rewrite 10Ks, can take out 1 over 2.5. Then it's S plus 2.5. I can take out also 1 over 6, S plus 6. Okay, they are the same. Then we can have 1 over 2.5 is 1 over 6. So 10 multiplied with 6 multiplied with 2.5. Okay. Over S plus 2.5, S plus 6. 60. 150. 150K. S plus 2.5, S plus 6. It is mentioned in the question, we want error less than 0.1. So we can choose 0.1. Okay, error 0.1 meaning KV, which is 1 over error, is 10. And we can use this value to determine K that we should use. KV, limit S to 0, SGS. And if we apply the formula here, the transfer function here, it is at 2.5, 6. K equal to 10. And K here is 10, 6, 2.5 over 150. It is 1. So K equal to 1. So this is the K that we should use in order to initially plot the bot plot. Use k equal to 1 to have the original bot plot. And here actually already given here k equal to 1. Okay, so this is the bot plot. We want to design phase margin 45 degrees. Desired phase margin 45 degrees. Actually, we want less than 45 degrees. Okay. So here you can see that sometime in the exam, in the problem, they will phase margin is given. Sometimes they are described. It is described in overshoot, or sometimes damping ratio. So we want 45 degrees. The original system, which is the uncompensated system. Uncompensated system. We need to obtain the phase margin. 0 dB is here. Okay, about 1, 2, 3, 4, about 4.5 here. Is here. Okay, more than 180 degrees. So 1, 2, 3, 4, 5, 9. So here, about perhaps about 6 degrees. Okay, you can check in your graph. I think 6 degrees. One box here actually 9 degrees. 6 degrees, and usually the phase margin is like this, right? From the phase here to 180 degrees, but now it is more than 180 degrees. It is 186 degrees. So the phase margin here is, we call negative 6 degrees because it is more than 180 degrees. If less, we can calculate it as positive. But if more than 180 degrees, in this case 186 degrees, I estimated. So phase margin for the original system is minus 6 degrees. Phase margin minus 6 degrees. Then we can start the first step. Actually, many steps earlier you have to do, but to start design, first we need to calculate the required phase equal to desired. We want 45 minus the original system minus 6 degrees, and we have to add a correction factor given as 5 degrees. Right? So it is 56 degrees. Okay, please be noted that the 6 degree here I estimated from the graph, from the box plot. You might have different value. We get 56 degree, the required phase. Then we can apply equation number 2. Equation 2 is phi max equal to inverse sine 1 minus beta 1 plus beta. Or 1 minus beta 1 plus beta is sine 56 degree. Equal to 0.8290. Then we can calculate for beta. 1 minus beta equal to 0.82901 plus beta. One minus beta equal to 0.8290 plus 0.8290 beta. Then beta equal to 1 minus 0.8290 over 1.8290. Please let me know if I make mistake. Zero point 0.0994. That is beta. Beta should be less than 1. We obtain 0.094. Let's proceed. Number 3, apply equation 3. Equation 3 is obtaining the gain, the magnitude at omega max. Is 1 over square root beta. 1 over square root 0.094 equal to 3.27, and in log, we need in log it is 10.29 dB. That is gain or magnitude at omega max. Any question up to here?
No, doctor.
Then step 4, we need to find omega max from the board plot. How to do it? How to obtain omega max? We need to use this value. Okay, we obtain JC, the maximum the gain at omega max we obtain as 10.29 dB. We need to locate the point with magnitude equal to minus 10.29 dB. Because we want to make sure this point become omega max. So minus 10.29 dB. Minus 10. From here, we can see this is 10 minus 10, 1, 2, 3. In the middle, it's about here. This is minus 10. Minus 10.2 minus 10 here. We go minus 10. Okay. It's about this point. Minus 10. Minus 10 dB. Okay, and if we check the value here, this is 1, 2, 3, 4, 5, 6, 7. 7 radian per second. Okay. Is a point where we obtain where the gain or the magnitude is minus 10 dB. And 7 radian per second now become omega max. Here is omega max. Omega maximum. This is the point that we will add, in which we want this point to be on the gain crossover frequency. So from the board plot, omega max is 7 radian per second. Then we can proceed to the next step, in which we can apply equation 1. Equation 1 say that omega max is equal to 1 over t square root beta is equal to 7. Then we can solve for t. T is 1 over 7 and beta. Beta 0.094. Zero 0.4659. That is T. Once we get T, we can get the lead compensator. 1 over beta, 1 over 0.094, S plus 1 over T. S plus 1 over beta T. Uh, 4659. Okay, beta T. Then you can proceed to get, you can rewrite this in a better form. Any question here?
No, doctor.
Number 7, you can finally, if needed, you can find the GS multiply with G lead. In the question, the question asks us to also, after obtaining the lead compensator, after designing the lead compensator, to sketch the compensated system. How can we do it? How can we do that? We have the original system. What you can do, you can plot, if required, you can plot this G lead. It is not difficult to plot. You can plot here. G lead will be something like this. Is something like this. Then you can just add at this point, just sketch. Here, no change. Then it will be slightly different after we add the lead compensator. Okay, so this is just sketching. But many marks is for the designing the lead compensator. I also have sent to you in the group, in the WhatsApp group, another example for the last year, for the last final exam last year, 1920. Also to design a lead compensator. Please have a look into this. We will do together in tomorrow for this particular example, final exam, and the board plot is given here. Okay, you please use this and try to design a lead compensator following the steps that we have gone through today.